Hello, in today's video we're going to be talking about Hess's Law. Now this is another one of those chemistry concepts that if you like Sudoku, the game Sudoku, you're going to really like Hess's Law. So for those of you who are really good at balancing equations, this is going to become easier for you than those of you who cannot balance equations quickly. We're going to be messing with equations, multiplying, dividing, flipping the equations, doing all sorts of stuff in order to find the enthalpy, the change in enthalpy of this reaction. Now what we know, we've already talked about, is E, the energy of the system, is equal to the work plus the heat of the system. But we know that we've canceled this out, so we can say that delta E is equal to Q. Okay? So this is, our energy change is going to be equal to the heat either absorbed or released by the system. Great. Now what is enthalpy? For this class, enthalpy is going to be approximately, these are squiggly equal signs, that's what that is supposed to be. That means approximately equal to. So the enthalpy of a reaction is going to be approximately equal to the delta E of the reaction, which is equal to Q. So in this case, the change in enthalpy of a reaction is going to be pretty much approximately equal to the heat evolved or absorbed by the system. So this is what we're going to be dealing with. We're going to be dealing with this term over here, enthalpy. We want to know the enthalpy of formation, the standard enthalpy of a reaction. So this is just a little background of what we've already done before. We know that energy has this work and heat term. We're going to be neglecting the work term this semester. Next semester we're going to be adding that in. It makes the math a little bit more tricky. But for this semester we're just going to say energy is equal to Q. And the change in energy is approximately equal to the change in enthalpy. Great. So what is Hess's law? What's the whole big deal behind Hess's law? Let's say I have an equation. Calcium, pure solid calcium, plus 1/2 oxygen gas is going to give you, plus CO2 gas is going to give you calcium carbonate, which is a solid. This is the standard formation equation. For the standard formation equation, we have to have 1 mole of product being produced, which means in this type of an equation, we can have fractions on the left-hand side of our equation. That's a little bit different than what we had before. This is a true balanced standardized equation. Standardized equation just means that we have 1 mole, we have to have a 1 subscript on our product. And that's what we have here. So this is our equation. Now, in laboratory, we have certain ways of measuring the heat evolved or absorbed by the system. However, in an equation like this, let's say that we didn't have this information given to us. We didn't have our instrument calibrated that day, so we don't know what delta H is for this equation. This happens a lot in laboratory. What we can do is we can go look in textbooks and find reactions that have all the parts of this reaction that have known enthalpies. So what does that mean? So you can look up in a textbook and we can see 2 different equations. Calcium solid plus 1/2 oxygen is going to give you calcium oxide. That's not what we're looking for, really. We want calcium carbonate. However, this has a lot of our reactants present. This is the standard equation, standard reaction for calcium and oxygen reacting together to make calcium oxide. And in the table, in your textbook, you will have delta H, the standard enthalpy of formation, for this equation to be negative 635.1 kilojoules. So we can look up in a textbook, we can see calcium plus 1/2 oxygen gives you calcium oxide, which is not exactly what we're looking for, but close, and we know what that enthalpy of formation is. Okay, we have to figure out another equation, or 2 or 3, that when we add up those 3 equations, or 2 equations, we will end up getting our overall reaction here. That is what Hess's law is. It is looking through textbooks, finding equations, standard enthalpy equations, standard formation equations, manipulating those equations in such a way that when you add them together, you get your equation that you're looking for. So let's see how this works. This is our equation that we want to get to. This is one of the equations that we're given. We're also given calcium carbonate decomposing into calcium oxide, that's a solid, as well as CO2, which is a gas. This delta H enthalpy is going to be 178.3 kilojoules. Okay, these are the only two standard reactions that we need to have. This has all of this here has everything present that we need for this equation to work. We have a calcium, we have an oxygen, we have a carbon dioxide, and we have a calcium carbonate. Some of them are not in the right order, and we have an extra one, we have this calcium oxide. However, we're going to try and add these two equations together in such a way that the calcium oxides cancel, and we have the calcium carbonate on the correct side. So let's see, how do we do this? We have certain rules. One of the rules, if we multiply any equation, let's say we needed to get rid of this half, so we would multiply everything by 2 in this equation. Hess's law states that the enthalpy of formation would also be doubled. So if we were to double this equation, we would double the enthalpy of formation. If we were to triple this equation, we would triple the enthalpy of formation. Okay, so that's one rule. If you multiply by a stoichiometric coefficient, you also multiply the enthalpy by that stoichiometric coefficient. Great. What's our second rule? If we flip the equation around, let's say we don't want the calcium carbonate on the left, we don't in this case, we want it on the right, and we were to flip this equation around, so let's do that. I'm going to take CO2 gas plus CaO solid. It's going to give you CaCO3 solid. So this is now gone. I've now flipped the equation around. If we flip an equation around, we change the sign of the enthalpy. So our enthalpy of formation is no longer 178.3. It is now negative 178.3 kilojoules. So those are our two different rules. If we multiply by a stoichiometric coefficient, we multiply the enthalpy by that stoichiometric coefficient. If we flip the equation, we flip the sign of the enthalpy. And what we want to do at the end is we want to be able to add up these equations such that we get our final equation at the end. And then if we end up getting this equation, we just add up the enthalpies and we get the total enthalpy of that reaction. So let's see how this works. So I'm going to add these equations together. Calcium, this equation number 1, equation number 2. I'm going to add those two together. So I'm going to get calcium solid plus 1/2 O2 gas plus CO2 gas plus calcium oxide solid. I just took all of the reactants, and then I'm going to produce calcium oxide solid and calcium carbonate solid. So these are the products: calcium oxide, calcium carbonate. These are the reactants: calcium, oxygen, carbon dioxide, and calcium oxide. Now we can start canceling out anything that's the same on the left and the right. We have a calcium oxide on the left. We have a calcium oxide on the right. Those cancel. So our true equation is going to be calcium plus 1/2 oxygen plus CO2 is going to give us calcium carbonate. That is our equation that we were looking for up here. So that means the delta H formation of this equation is going to be negative 635.1 kilojoules plus negative 178.3 kilojoules. All I did was I added up the two different enthalpies of formation for these two equations, and I get a new delta H formation of negative 813.4 kilojoules. So now we know that this enthalpy of formation for this equation is negative 813.4 kilojoules. That is what Hess's law is. It's using equations with known enthalpies of formation, manipulating those equations in such a way that when we add them together, we get our final unknown equation's enthalpy. And so when I'm saying Sudoku, this is an easy example. This only has two different equations. Some of these have 4, 5, 6 equations. where you're going to have to be multiplying by a stoichiometric coefficient. You're going to have to be flipping the equations around and adding them together. So this is a simple example. We will be performing a lot of these in class tomorrow, so don't worry if you don't understand how this is working. And I will see you all in class tomorrow.